Okay, so today I want to talk about crossing numbers. So this is a very, very nice topic with some really cool proofs. Neither of these are in, this is in neither of the two books we've got here, okay? So the idea with crossing numbers is, suppose you have a graph that's not planar, then you can't draw it without crossings, right? There have to be crossings. That's what it means to not be planar. But a natural question is, well, what's the best we can do, right? Let's draw it with as few crossings as possible, okay? So if G is not planar, then how few crossings can we? Oh yeah, no floor function on number 2, Ethan. Yeah, thanks, Eric. If you just re-download the homework sets, the typos are fixed now too. So like yeah. So how few draws can we get in a drawing in the plane? Okay, this is the crossing number denoted CR of G. Okay, so for instance, the crossing number of like a K4 of an actual planar graph is 0, because you can draw it without crossings, right? So when a graph has crossing number 0, that's equivalent to it being planar. Okay, so planar if and only if crossing number G is 0. But for graphs that are not planar, we want to minimize crossings. So another example would be K33, right? K33 is not planar. We know we have to have crossings when we draw it. How few can we have? Well, one drawing, just sort of like the canonical obvious way to draw, is to set the vertices on 2 sides here and just draw straight lines between them, right? So this is joined to all these. This is joined to all these. And this is joined to all these. And then if you go and look at this picture, you find a fair amount of crossings. The picture is not optimal here, but 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe there's 9 crossings there or something like that. Okay. But you can definitely do better than this. Let me just keep the same orientation of vertices in the plane, and let's try and draw this and keep the number of crossings low. Okay. Now we know, and it's not that important, we know if we don't have to be concerned with straight line embeddings, right? We know they exist. Actually, you can prove that you can, well, okay, let's not dwell on that. It's actually important for now not to necessarily draw straight lines. Yeah, so let's go here. And then where else does it? Okay, so this one, what's up with my picture here? I see. This one needs to go here and down here. Let's just check vertex by vertex. Okay, this says degree 3 goes to everything on the left-hand side. It's fine. This one has degree 2, still needs to go to this vertex, but that's fine there. This one has degree 1, needs to go to all 3 of these. I was hoping I can get away with 1 crossing. I should be able to. What am I missing here? Okay, I see. Let's do a little better here. Go like this, and then here's 1 crossing here. Okay, 1 crossing. There's no way we can do better. K33 is not planar, right? You can't have fewer than 1 crossing. So this actually proves that the crossing number of K33 is equal to 1, because it has to be greater than 0, and obviously the number of crossings is an integer. Okay, so that was the minimal one there. And like, planar graphs, if you want to find the smallest, you need to establish a drawing with few crossings and then show you can't possibly do fewer. That's the hard part. How do you prove that you can't do better? Well, for this one, we know it's not planar, so we know it can't be 0. But for something more complicated, like proving that it can be done with fewer is challenging. That's the difficulty. Okay, so to make the concept of crossing numbers a little bit more rigorous, we should deny the following scenarios. Okay, so we require the following facts in one of these drawings here. So no edge crosses itself. Okay, so the forbidden picture is something like this. You can't have that. Just locally here, looking at this edge, it's very unlikely you'd ever want to do such a thing, right? I mean, it's pretty clear you can get rid of this crossing. So edges that have a common vertex, incident edges won't cross either. Incident edges do not cross. So if I have an edge here and another edge that's incident to the same vertex, this scenario never happens either. This one's clearly easy to undo, but it's less immediately clear like that you can always fix this if it occurs, right? Like maybe there was some reason to need to do this. Okay, and then the third one here is that edges don't cross twice. Okay, so if you do have a crossing, here's one edge, and then you have another edge like this, it doesn't cross over 2 times like this. Okay, so I want to forbid all these situations. Now, it's not immediately clear that you can even do this and keep the number low, but it's an exercise, right? So via exercise, we can show all these can be avoided. Okay, so that's really what's saying. Not only these forbidden, we can actually avoid them. So if I told you I have a drawing of my graph and it has the fewest crossings possible, you can rule out any of these things happening. Okay, so if any of these happen, you can reduce the number of crossings, somehow getting rid of these without increasing crossings somewhere else. Okay, so that's an exercise. Also, let me mention that generally we're not going to allow 3 like crossings to happen at the same point. We're not going to allow 3 edges to cross at the same point. You can allow it. It just makes things complicated. So don't allow 3 crossings or 3 edges intersect at a point. So we don't want to have this picture either. But this is not like forbidden. So 2 things. One, we can easily undo this, right? If this happens, just shift the edges ever so slightly around that central point so that you have separate crossings. But like this doesn't mean there's less crossings. This is 3 crossings, right? It's 1 point, but we're not counting the points where the crosses occur. We're counting the number of times that an edge crosses another edge here. And with ruling out like this one here, for instance, especially, then this is well defined and it's clearly 3. There's 3 pairs of edges crossing at this point here. Whether I draw them on top of each other or not doesn't change anything. But if I'm trying to illustrate, I'll want to avoid this because like, how do I, it's hard to mark this 3 times. But that's just like a quality of life, you might call it, or something. I don't know. Okay, so I want to talk about the complete bipartite graph case again here. So this was K33. And I want to look more generally at the crossing number of KAB, right? So if I have A vertices on one side and B vertices on the other side, how few crossings can I get? Obviously, KAB contains K33 inside of it, as long as A and B are large enough. So in general, it will not be planar. We'll have to have some crossings. And the question is, how can we keep the number of crossings low? And this question actually has a really fascinating history to it. So in 1944, Paul Turán, who was an amazing graph theorist, who we'll hear about later, was actually working in a forced labor camp where they had these kilns that created bricks, right? They fired bricks in these kilns, and then they took these like railroad tracks and filled up carts and moved them over to 3 other locations. I don't know what the exact numbers were, where they collected these up. These were like storage spots. So you have like kilns and storage. And the arrangement looks something like this. And it had train tracks between them, just like this, just like a K33. So you could bring these, you fill up your cart with stones, with bricks, and push them across. And when they were doing this work, he said that the crossing points of these tracks were pretty unstable, and often the cart would like jump the tracks when it went to these crossings. They just weren't well designed, and it dropped bricks off, and you had to pick them up, and it was a huge pain. And so while he was doing this work, he thought about, well, would there be a better way in principle? Like if we rearrange the kilns and the storage in a different fashion, could we reduce the number of crossings of these things? Now, this wasn't going to be implemented, obviously, but he was a mathematician and couldn't help himself. And so he solved it for K33. He figured out like a better way of drawing it. Now, this picture on the left here isn't the solution, right? The train tracks should be straight, right? So we don't have these curved lines. So he came up with something else, and this is called Turán's brickyard problem, or the brick problem. And so we'll look at a larger example, because what do? You generalize. So he said later, after the war, in something like 52, he actually thought about this as an actual mathematics problem and looked at, well, okay, now I have A, kilns, and B, storage places. You know, how many ways can I draw these tracks and keep the number of crossings reduced? And then he actually, so he proved the following theorem. And let me show it to you here. Okay, so theorem. Let me just write it very simply here. The crossing number of the complete bipartite KAB, so you've got A vertices in one class, B vertices in the other class, is at most A over 2 floor times A minus 1 over 2 floor times B over 2 floor times B minus 1 over 2 floor. That's the upper bound. Okay, so roughly A squared over 4 times B squared over 4, just roughly, especially for large A and large B. Okay, that's the upper bound on the crossing number. So let's think for a second. How do you get an upper bound on a crossing number? Well, if you draw it and it has this many crossings, that's an upper bound, because maybe you can do better, but this is definitely, there's no reason to have more crossings than this if I can actually give you an example where we do this. Okay, so the upper bounds and crossing numbers are given by basically by a drawing, and lower bound is given by, hey, you can't do better than this somehow. Okay. All right, so let's look at the proof. And it doesn't really change the configuration I'm going to give you, but I'm going to just, for simplicity, say A and B are even. Okay, so both are even. Other cases are basically the same. In fact, the construction's the same, it's just the algebra at the end. Okay, and so Turán came up with this very, very simple arrangement. We're going to imagine that we're in like R2. We've got the x-axis and the y-axis here. And what I'm going to do here is draw A points, A half, sorry, here. So A half, put A half of them above the origin, and A over 2 of them below the origin. And then do the same with the B vertices along the, that's y-axis, sorry, and along the x-axis. I don't know, say B is a little bit smaller, B over 2 and B over 2. Okay. Did I 1, 2, 3, 4, 5, 1, 2, 3, 4. Okay, so that's how I draw my picture. And then what are the edges in this picture? Well, every red point goes to every blue point, right? I've just drawn it in this fashion here. So I'm not going to fill in the whole thing, obviously, but this point goes to these. These should be straight lines, despite the fact that my picture won't be. 3, 1, 2, 3. Okay, it's getting pretty awful, but we're not going to argue it by counting in this actual picture, obviously. And then like this. And then the nice thing is the other quadrants obviously look the same, right? So as long as I understand what's going on in the quadrant 1, then it's the same for the other things. Like this, an edge from this guy to this guy here is not going to cross an edge in any other quadrant. All my edges are restricted to quadrants, okay? So then what I want to do here is just, let's count crossings. Okay, so how many crossings are there in this picture? Well, 4 times whatever I count in the first quadrant, because there's 4 quadrants. Okay, so how many crossings do I have here? Well, what does a crossing look like always? A crossing always looks like it's, let's actually, it's 2 vertices on the y-axis and 2 on the x, because I need 2 edges in order to have a crossing, right? If you have 2 edges, you have a crossing. We know that 2 edges that are incident, that share a vertex, don't cross. We know that by rule, but we also know if you look at this picture, if I take 2 edges coming out of this point, they obviously can't cross, right? Because they just stretch further and further out on the x. So I have to have a point here and a point here, and then a point here and a point here. Those 4 vertices define 4 edges, and 2 of those 4 edges cross, right? If I take these 4 vertices here, this guy goes to here and here, and this one goes here and here, and there's 1 crossing here. So 4 vertices, 2 on the x-axis and 2 on the, 2 on the x-axis and 2 on the y-axis define exactly 1 crossing there. Okay, so among the ones above the x-axis that are on the y-axis there, if I take A over 2, choose 2 of them, and then take B over 2, choose 2 here, so choose 2 from here, choose 2 from here, they'll define exactly 1 crossing, right? They define 4 edges, which can give 1 crossing here. Okay, and because we're a little bit limited in time here, if you work this out for A and B, even or odd, or all the different examples, you get exactly this quantity here, right? What is this very, very roughly? Well, the 2 here and the 2 here cancel with the 4 when I take the choose function, and I have A over 2 times A over 2 minus 1, and B over 2 times B over 2 minus 1. And depending on parity, those numbers are equivalent to these these floor functions here. This is just a little bit cleaner way to write it. Actually, this could be your solution. The only issue is if A is odd or B is odd, then you have to count more carefully, because then it's not exactly half above and half below. It's half above rounded down, half above rounded up. And then the 4 quadrants are not exactly the same. They're like close. Like, you just have to check all the individual things. But basically, this is the full argument. The rest of it's a little bit tedious. But it's a very simple construction. Okay, that comes out to this. This is when A and B even. Okay, when A and B are odd, the exact count is not this, but you still arrive at the right-hand side here. Okay, all right. And so something that's very interesting here is that the conjecture is that you can't do better. Okay, so that's Turán's brickyard conjecture, is that we believe you can't do better. So conjecture is that there's equality here, that there's no better drawing than this drawing here. Okay, and in general, we don't know whether that's true or not. But we do know it's for small values, right? We know it when A and B are small, because you can, use the computer to maybe help you out and show you can't do better, or you can prove it individually. But there's open cases. So the first open case is for, well, there's kind of 2. Case 7, 11 isn't known. I don't know what these numbers come out to. You work them out. But for 7 and 11, this tells you how many crossings you get in this picture here. And we don't know if there's a better way to do it. Like for this concrete example, maybe there's a better way to do it, maybe not. And also K9, 9, that's a little more balanced. These are 2 specific instances where we don't know if you can do better than this guy here. The reason it's difficult is you probably can't do better. So it's not a matter of lack of trying to get a prettier picture. It's somehow showing no matter what you do, you're not going to get fewer crossings than if you just drew it this way. Okay. But the real gem would be to actually prove that you have equality here for everything, not just for 7, 11, and 9, 9, although those are already interesting in their own right. Okay, so let's prove, excuse me. Let's get a lower bound for crossing numbers, right? So how small can you get a crossing number in general? This argument is awesome. Okay, so it's a proposition. By the way, maybe mentioning one thing. So you can ask for crossing number bounds of this type for any sorts of graphs. One interesting direction where we don't have a theorem either is when the crossing number of a complete graph, right? A K100, say. Obviously, you're going to have crossings. K100 contains K5, and it's going to have a fair amount of crossings, but there should be some nice way to draw it to minimize the number of crossings. There's a conjecture stated in the notes that says what we believe that number to be true, but it remains open. We can't show that you can't do better than what's suggested. Getting the upper bound there is a little bit harder. Anyway, so complete graphs are still open. Crossing number values are very much open questions still. Okay, so the proposition here is going to be crossing number lower bound. So this is our general lower bound for crossing numbers. Okay, so let G be an n vertex m edge graph. So we have n vertices and m edges. Then the crossing number is bounded below, it can't be too small, by m minus 3n plus 6. Okay, so the number of edges minus 3 times n plus 6. What's familiar in this statement here? What's familiar in this statement here?
3n plus 6 was our bound on, or from before, for planarity.
Yeah, 3n minus 6, right? 3n,
oh, yeah.
but it makes sense, right? That's so what this is saying actually is that the crossing number is it's bounded below by the difference between the number of edges and the most edges you could have in a planar graph, which is somehow like a reasonable bound, right? It's for each edge you go above the most you can have in a planar graph, you're getting at least one more crossing. right? Which is reasonable. In fact, that statement almost sounds like isn't that the proof? Like it almost, and it actually it almost is. It almost is, right? So this is what this is saying is each new. Well, okay, I don't want to. I don't know how to write that like any better than the way that I just said it there. So let's just leave it at that. I'm going to prove this though. The proof's really cool. Okay, so and actually, by the way, this doesn't contradict the planarity, right? If my graph is planar, then this bound will be 0, right? It'll say that if I have at most 3n minus 6 edges as a result of being planar, then this holds. The problem is there are graphs with 3n minus 6 edges that are not planar, and then this just gives a lower bound of 0. For instance, I think if you plug in k33 to this, which we know has crossing number 1, this lower bound doesn't give us anything useful, because for k33 we have 9 edges, and then we subtract 9 and add what am I missing here? Something's dreadfully wrong. k33 has 6 vertices. So yeah, we get 9 minus 18 plus 6. Oh, that's negative, right? Okay, that's okay. So lower bound is, yeah, that doesn't help us, right? It just says we have at least 0. Obviously, that's always a lower bound on the number of crossings. So it doesn't tell us the truth. This is weak in general. So yeah, Ethan, good question. How hard is it to find a maximal planar? Oh, maximal planar subgraph. Okay, so subgraph, that's tricky. So maximal planar meant that you can't add edges to it, right? And so to find a maximal planar subgraph, one, there may not be a maximal planar subgraph, right? Imagine your planar graph is a giant cycle. Every subgraph of that will not be maximal. And so to actually search for whether it has a maximal subgraph that's planar, I'm not sure. I don't know. So yeah, I'm not sure. Huh, it's a good question. It's a good question. Now you can turn a graph maximal planar by adding edges. That's easy. But yeah. All right. So let's figure out this lower bound. So let's suppose we've drawn G with as few crossings as possible. Okay. So we got G, it's drawn on the plane, it's drawn with as many few crossings as possible. And I'm going to introduce this auxiliary graph that I build from it. Okay. So introduce an auxiliary graph H. Okay. Let me just say here, this term auxiliary, it doesn't have any formal meaning. It just means we're building a graph that has something to do with the original graph, but it's not necessarily a subgraph. It just records some information about the graph. So it's kind of a filler word to remind you what's going on. And all we do is at every crossing in the drawing of G, that crossing we're going to transform into a vertex and just make the edges be in the natural way. I'll draw an example. Making this formal is obnoxious. So by adding a vertex to G at each crossing, and making the natural, what did I say here? Incidences, something like that. Let me give an example. So say I drew K33 with 1 crossing. Okay, I have to replicate this picture. It's maybe this is overkill. Anyway. I think I got them all here. So this is G here, and I drew it with the fewest crossings possible. I drew it with 1 crossing, and all I do is introduce a new vertex there to make H, and then obviously each edge that's split by that vertex, this is now new. These are new, right? This is a new edge. This is an edge. This is an edge. This is an edge. Those 2 edges became 4 edges at the crossing. Okay. So do the thing that on the first day of graph theory I tell you is not a thing. Right? When edges are crossing each other, that doesn't mean there's a vertex there, but let's do it now. Let's introduce a vertex there. Okay. So let's make some observations here. What can you tell me about H? H is planar, right? Like, and the picture certainly tells you it, but there's no crossings. If there was a crossing, it's now a vertex where edges meet. So all the crossings have been eliminated. So H is planar. Excellent. How many vertices are in H? Well, as many as there were plus the crossing number of G, right? We introduced a new vertex for each crossing. And then how many edges are in H? As many as we had before, plus how many new edges are introduced? This is a little tricky here. Let's look at our example here. Here I had 2 edges, and they transformed into 4 edges, right? Whenever you have a crossing, yes, good, Ethan, exactly. 2 times the number of crossings. Each crossing introduces 2 new edges, right? 2 becomes 4. Or you can think of like there's this edge and there's this edge, and you like chop it. You kind of shrink the original edge and then add on these 2 new segments here if you like. So you add 2 new edges for each crossing. So 2 times the crossing number of G. Okay. And now we have everything that we need because now we can just use the planar edge bound. H is planar, so the number of edges in H is bounded above by 3 times the number of vertices in H minus 6, right? So as H planar. And then this is a 6, not a G. And then if you just plug in these values here, if you plug in this for E of H and this for for V of H, then that gives the solution, okay? Substitute, that's ugly. Substitute and solve for the crossing number of G to get the proposition. That's the end of the proof. Okay, I won't do the arithmetic there because I want to get through the other proof. But notice when I substitute in for V of H, nothing depending on H exists anymore, right? I'll have an N, I'll have an M, I'll have crossing number of G, and I'll have 2 times crossing number of G. Actually, in total, you have 3 times crossing number of G. And yes, if you solve for, you'll have crossing number of G on the right-hand side here, positive, and you just solve, you get the other values there, okay? Anyway, simple, but like really cool. Like that's a cool proof, right? Just draw the vertex there, you magically get it planar and use the planar edge bound and get it bound there. And you can see kind of intuitively then why this kind of proves that the argument we kind of felt like drawing edges above this bound here seems to introduce crossings. And so we get, for each one, like it basically makes sense. Like if you added an edge and it didn't create a crossing, then like, why didn't you, like you didn't, like the bigger graph was planar, right? Like makes it maximal planar and then add on. So it's just the question is maybe like after adding 500 edges, the 501st edge didn't actually need to introduce a crossing, right? Because it was already not planar. So we don't necessarily get crossings later on, but this shows that we should. Okay, so now let me tell something called the crossing lemma. This is a general upper bound on crossing numbers. Okay, so crossing lemma. Yes, this is somewhat common. I'm stating this as a theorem, but its name is lemma. So it was used to prove something else. But now when you talk about crossing numbers, like this is one of the sort of central theorems of crossing numbers. So it says something about crossing numbers. Okay, so let G be a, okay, simple. I don't know why I put this in the notes to emphasize graph with, so simple just means no multi-edges. N vertices and M edges. Sorry. And M has to be at least 4 times N. Okay, so we have at least 4 times as many edges as vertices. So we're definitely past the threshold for being non-planar. And the proof doesn't work for smaller values here. So you need this theorem only works in this range here. Okay. All right, then the crossing number of G is bounded below by 1/64. This isn't really important here. What's important here is the number of edges cubed over the number of vertices squared. That's my general lower bound on crossing numbers here. Okay. Kind of a weird looking number here, but let's actually compare to what we know about the crossing number of KAB. Okay, so the crossing number of KAB that we got before was very roughly a squared b squared over 4. Sorry, over 16. The constant on the bottom doesn't matter here, right? It's a over 2 floor times a over 2 minus 1 floor, b over 2 floor. So we get a squared b squared and then over some constant here. But if we try to plug that in for this guy here, we get, so the crossing lemma says the following, that this should be at least 1 over 64 m cubed over n cubed. But this equals 1 over 64. Oh yeah, okay, let's say a and, okay, maybe to make life a little bit easier, let's say a and b are both equal to n over 2. Okay, or equal, let's say they're both equal to n, just so that they're equal to each other is the point. So I have an KNN or KAA. So this is, yeah, let's actually just erase to do this. So okay, just so we can actually compare. So if we KAA, then it's a squared times a squared. So a to the 4th over 16. And then here we have 1 over 64. M cubed is the number of edges cubed. How many edges are in a KAA? A squared. So it's a squared cubed. And then over how many vertices? A, and then squared. And this comes out to be 1 over 64, a to the 4th. So like order of magnitude matches, right? They both say it's about a to the 4th many crossings. Yeah, this is over 16 as my upper bound and over 64 as a lower bound. So there's a gap in constants there. But what it says is that the crossing lemma, at least for complete bipartite graphs, it's like the right ballpark, okay? In general, we don't know the truth for crossing numbers. Like we don't know the answer, and this is not always a good estimate, but it is a reasonable estimate for this guy here. Okay, so let's give a proof of this. And this is another proof by the probabilistic method. We're going to do a random technique here to find that this bound holds in general here. Although in some ways it's an even easier random method than we've used before. Okay, so generally how all arguments go when you're trying to prove a lower bound on a crossing number is say, hey, draw it with CR crosses. Draw it with as few crosses as possible and start analyzing. Try to find, hey, you definitely have a crossing here and a crossing there and a crossing how that, and then you get a bound. Okay, so draw G with the fewest number of crossings. Okay, we'll arrive at the bound at the end there anyway. Okay, and now let's fix a probability P between 0 and 1. Okay, we'll determine it at the end of the proof there. Actually, I won't determine it. I'll just tell you how we arrive at it. But so we're going to choose some probability. And here's what my experiment is. I'm going to choose vertices at random from the drawing of G. So with probability P, I examine a vertex and then flip a coin, biased coin, and keep that vertex or not with probability P. Okay, so select vertices of G, each with probability P. Okay, this obviously creates a probability space here. I'm not going to go into the full details there, but this is an easy to understand experiment here. And let GP be the induced subgraph. I have to explain what I'm talking about here, of those vertices selected. Okay, I've actually avoided to this point talking about what an induced subgraph is. Let me briefly explain it here. You may have come across it in the notes. So there are subgraphs and there are certain types of subgraphs that are called induced subgraphs. All I mean here is when I select these vertices with probability P, I'm going to maintain all the edges that are on those vertices. Okay, so I'm not throwing away edges except those that have a vertex not selected. So if I selected 3 vertices and there were some edges among them in the original graph, I just keep all the edges. Okay, so induced means inherit all edges from G. All the edges that were incident to the vertices selected are maintained. Okay, so it's just highlighting a part of the graph and saying, oh, I picked these ones randomly, keep everything that was on there. Okay, so now that we have this very simple experiment, let's record a little bit of information. So let n sub p, m sub p, and x sub p be the random variables recording number of vertices of this randomly constructed graph, the number of edges of this randomly constructed graph, and the number of crossings of GP. Okay, so let me emphasize something here. So number of vertices that'll be easy to compute the expectation there, obviously, but that's the number of vertices we kept, right? So if I do this procedure, I keep a certain number of vertices depending on how my coin flip turns up. I also keep a certain number of edges. I'm also going to keep whatever crossings I get. I'm not going to change the drawing. So I have my drawing and I randomly select vertices of it. And if some edges were selected by this procedure that have a crossing, I keep that crossing. Keep in mind, the crossing number of this thing may drop, but I want to keep the crossings that were actually there, right? If I grab some random vertices, maybe the drawing can be redone to avoid crossings. That's not what I'm doing. I'm just keeping the drawing as it is. I'm just throwing away parts of it. In fact, in some ways, maybe it's even easier to restate this problem. Instead of keeping vertices with probability p, I'm throwing away vertices with probability 1 minus p and just leaving the picture unaltered otherwise. You can visualize it that way if you like. And then actually, if you do that, then you don't have to discuss the notion of induced anymore. It's obviously what you just keep everything that's left over. But anyhow, okay. So let's compute the expectations of these values here. So the expectation of n sub p, which is the number of vertices in GP, what's the expectation? What's the average number of vertices we're going to get here? I mean, technically this requires some familiarity with probability theory, but it's pretty simple. What's the expected number of vertices? Yeah, good, Eric and Ethan. P times n, right? For each vertex n, we flip a biased coin p, and so we keep p times n of them. Okay. Okay, this one's a little more interesting. What's the expectation of the number of edges? What's the expected number of edges? When do you keep an edge in this procedure? Here's why describing it this way is a little more valuable. So you keep an edge if both n vertices are kept, right? If either of these vertices is deleted or not chosen, then the edge does not remain. So each edge, what's the probability that edge is kept?
Is it like p squared times n choose 2?
Just p squared. Yeah. So
Okay.
yeah. So Van times m, right? M is the actual number of edges, and for each edge,
okay, yeah.
I have to win the experiment.
I get
If the graph was complete, then yeah, absolutely, it'd be that. Or like if I'm creating a random graph, it would be something like that. But yeah, but here, yeah, here it's each edge, its chance to be maintained is if both endpoints were maintained. And then we can use a similar idea to figure out the expectation of xp. So xp is the number of crossings in this drawing here. When do we keep a crossing, right? We're not going to introduce crossings by doing this procedure. We're simply going to keep crossings or not. And when do we keep a crossing? We keep a crossing if the two edges, yes, Ethan, exactly. If we keep both edges, right? And how do we keep both edges? If we keep all 4 vertices corresponding to those edges. This relies on those early facts we talked about crossings, right? If this was an allowed crossing, then you have to talk about keeping the 3 vertices, not the 4 vertices. And then it would be, things would be problematic. But we don't allow this scenario. And so a crossing corresponds to 2 edges, which corresponds to 4 vertices. And so each crossing, of which there are CRG, we keep it with probability p to the 4th. All 4 vertices are maintained, okay? So these 4 expectations are nice and easy to compute based on the number of vertices. Okay, all right. Now we use the crossing lower bound. So crossing number lower bound proposition says the following, that the crossing number of, say GP, well, let me say like G, I don't know, let's say F. Any graph F. I don't want to use G because we're talking about a graph G. I don't want to use H because that was the graph in the proof of the proposition. I don't want to use GP because, well, I mean, I guess it can. But this is always the number of vertices in F plus 3 times the number of edges in F. Number of edges in F plus 3 times the number of vertices in F. This is always at least 0. All I've done here was, move the crossing number. Or we know crossing number is greater than or equal to, what's wrong here? Sorry. This is even weaker than the crossing number lower bound. Normally, crossing number lower bound says crossing number is greater than or equal to m minus 3n plus 6. If you bring these things over to the left-hand side, you get the crossing number minus edges plus 3 times vertices is greater than or equal to, well, actually 6, not 0. But the plus 6 is not going to make, it's not going to, my bound can be improved by adding 6 to it at the end, you'll see, but we don't care about that. Okay. So this just follows from the thing. That the point is that quantity is always positive or non-negative. Actually, it's always positive because it's at least 6. But okay, so that means that the expected value of xp, that's a big xp. So the average, the xp is the crossing number of gp. Yeah, maybe I should have said this for gp. So in particular, this holds for gp. So this minus mp plus 3 NP, this is greater than or equal to 0, right? The average, so for each of these graphs individually, the computation of what's inside the expectation is greater than or equal to 0. So the average, which is the expectation of these, is greater than or equal to 0, obviously, right? If they're all non-negative, then the average is non-negative. Now, by linearity of expectation, I can rewrite this whole thing as the expectation of xp minus the expectation of mp plus whatever. I mean, I can put through, I don't know, 3 times the expectation of np. It doesn't matter if I take that out or not. But I just computed each of these values, right? This is p to the 4th crossing number of g minus p squared m plus 3 times pn. And this is all just it's greater than or equal to 0. Just let me put it over here to remind ourselves. Okay. Now we solve for the crossing number of g and get the following, lower bound, right? The crossing number of g appears in this statement here. So we can solve for CRG, move these over to the right-hand side, divide both sides by p to the 4th. We get p squared m minus 3pn over p to the 4th. It's not really important, but this can be simplified to m over p squared minus 3 np cubed, right? And now notice what we have here. We have a lower bound on the crossing number of g that holds. It has nothing to do with anything we argued before anymore. This is how we arrived at this, but I wrote down a statement for you. Crossing number of g is greater than or equal to this quantity here. And this holds for any p between 0 and 1, right? P can be like any probability this thing's going to hold. So all I have to do is optimize, right? This holds for any p. So all I need to do is choose the best p to maximize this, right? Because the crossing number is greater than or equal to this for every p. So find the p that makes this right-hand side as large as possible, thus giving me the best lower bound. And that's just calculus. And this, which p comes out to 4n over m. That's the best p, okay? Remember at the beginning, I said that m was at least 4 times n. So that means that this is at most 1, okay? As m was at least 4 times n. So it's a valid quantity for a probability, okay? So the proof still works even if I'm outside of this range here, right? Everything will still work. We only use this at the end. It's just that the maximal value p is maximized at a quantity we can't achieve. And so you just have to take some other p that's not smaller and the answer is ugly. But as long as we can get p to this thing, we get the optimal. Once you figure this out, so obviously I'm not going to do this, but it's just simple calculus. If you plug that p into here, you'll get exactly what we want. Okay, this P gives that the crossing number of G is at least 1/64 m cubed over n squared. Okay, that's the end of the proof there. Okay, that's a lovely one as well. This is a fantastic proof. And what's cool about it, I mean, like a lot of probabilistic proofs, we use the expectation to prove the existence of something, right? We say, hey, the expectation of this occurring was, you know, greater than or equal to 12. So there exists a graph with greater than or equal to 12 occurrences of this thing here. Here we didn't do this. Here we didn't prove the existence of anything, right? We just said that we just used this computation of the expectation to get a concrete bound on the crossing number and said, well, the crossing can't get the crossing number smaller than this because of our experiment here, no matter what. There's no, like, at this point, there's no randomness anymore. P is just a number, right? Which is kind of cool. This is, though, often how proofs of where we're not making a construction, right? I didn't try to create you a graph with lots of crossings. I just said any graph will have at least this many crossings. And I sampled this randomly. Of course, you can unfold this proof and try to argue in a counting fashion without expectation. But, you know, why? Like, this is, you know, this is good this way. Okay, good. So that's it for the day.